Okay, we're ready. I think we'll get started again. Let the cats out. The cats got out of the room.
Where's Mark when you need him? Mark!
I think it would just start.
Okay, we're gonna get going again. I'm Scott.
Okay, guys, can we get quiet and please get take a seat if you want to listen, if you want to check out this presentation. And please close the doors.
You know you're running against the schedule by half an hour.
Oh, we're ahead of schedule.
Half an
Should
hour.
we wait? What should we do? I was supposed to be 2:30. That was the original.
No, it was 3 o'clock, but I thought you were.
Mark's going to pose. I'm going to flesh the talk out with more than just slides and words, and post it in the article section on the audio. And I hope Jan could post it also on his site.
Yep.
You're welcome to.
I'll
Yeah.
sure do that.
Okay. All right. Get going. Okay. I'm going to talk briefly. A simple, brief history of analog computing. It's going to be. I have some cute slides, and it's going to go way back. And then I'm going to cover the history of commercial discrete op amps. I was lucky enough to get some reverse engineering schematics from the 80s, so I can provide a lot of discrete op amp schematics with all the values there, and several designs of the same product from different companies. And people can take those with them and take them offline and maybe learn something from them. I'll try to go through them. And I have a discrete op amp for audio that was part of a thread. And I haven't been able to, I didn't get to do another prototype of this, but I'll present what I did and I'll go through the circuit. But I do intend to build another prototype and come up with a layout and some boards. And I don't know what Mark wants to do with those, but we'll think of something. Okay, analog computing dates from 87 BCE. I don't know, anyone here ever heard of the Antikythera mechanism?
Yes.
Yeah. I think Tom Lee stole this from me because I did it years before. Anyway, this thing is an incredible mechanical computer, and it gave people great power to know what's going to happen in the heavens. And you all see the movies with someone predicts the eclipse and everybody bows to them. So that's basically the first analog computer. And what's also interesting, which you don't always find out, is that this was completely lost to Western civilization. And it came back because in the Islamic countries, science was great. In the Christian countries, science was sort of like alchemy and mystical. So actually, this idea was saved and came back to our culture later. Okay. Calculus, integration, differentiation, addition, subtraction. You can see the basic op amp symbol is really old. These drawings are from very old textbooks. And basically, people made analog computers by putting these simple blocks together to solve differential equations using calculus. In the 1800s, they actually made these things mechanically. And I don't have any pictures of the actual things, but they're just incredible. These things were good to 0.1%. You can make a mechanical friction wheel integrator good to 0.1%. And someone told me, I didn't have a chance to get a picture, that someone built a Fourier transformer like with these things. So you can do a Fourier transform completely mechanically by turning the knobs and everything. So I actually have a textbook showing how to build these things, and they became very involved at times. Thanks. Okay, so for the war effort, Vannevar R. Bush from MIT brought a lot of money to MIT. They built these huge differential analyzers, and they did artillery tables because the actual heavy artillery equations are extremely complicated. They have to take into account Coriolis force and all kinds of things. And they used to have French mathematicians sitting at tables doing it all by hand. So this was a part of the war effort. That's all right, go to the next one. I love this guy. This is a German, this is after the war, but until 1968 they were still using a 61 coefficient Kite computer, and I don't know what German port. This is from a German North Sea port. And that's just before you could probably buy a PC to do it, or a small computer to do it. Next one. Okay, this is a big analog computer. I don't know if it's that clear from where you're sitting, but the thing was called TRIDAC, Tri-Dimensional Analog Computer. And this was to simulate an entire, like a bomber in flight. And you can see those catwalks. That building's as big as this building. And it has hydraulic pump rooms and transformer rooms, generator rooms. And if you look up TRIDAC on the web, you'll find a whole article with pictures of the people with the oscilloscopes and things. And it was an incredible wartime project in the UK. Next. I love this picture too. This is perfect. This is 1950s America. That's the first, Jan, see pictures of that. That's the Gap R model tube op amp. And here you can see them being used in a flight simulator with someone, programming it with the, like a, do a telephone switchboard. And there's a guy who looks a little bit like Colonel Hogan there. All right, next. That's the schematic. Very simple. Differential stage, another gain stage, follower output, plus or minus 300 volts. It has a ground reference that op amps really don't need, but this had it. And it's got your differential inputs. That's basically start of the basic start of the simple op amp that you can just build things with. Next one. Okay, now in 1963, Bob Pease was working at Teledyne Philbrick, and you can see how close, in some ways, this was to that tube op amp. This is a very primitive solid-state op amp. It's got two differential gain stages and an output stage, and this was a pretty good op amp. And it came on a little card you plug into your manifold, just like the tubes were in that manifold. And so, by 1963, they were moving towards doing it this way. Next one. Okay, bring audio into play. Dick Berwin claims he's helped start Analog Devices to make op amps for his stereo. He'll say that too. Anyway, this is one of his designs. Again, it's still two differential stages. You can see the inductors in the input to get the transconductance very high at low frequencies, and it's easier to compensate because now the GM goes up goes down at high frequencies. This was a compensation trick that actually the JE, I don't think everybody, but a lot of people have seen the JE 990 and read that article. That's basically where this came from. Next. Okay, typically those things went into bricks like that, and everyone's sort of seen those around somewhere in some history book or on somebody's bench. The pins came off the bottom, and that whole amplifier circuitry was all potted in there, hopefully so people couldn't see what was in there, as well as to protect it. Next. And then this is an early chip and wire. This, in fact, I think was a Haas 50, which is a very famous, one of the most successful discrete op amps. I'll have some schematics of that later. And that gives you the scale of this package. This, I think, is the T08 style. There was a T03 style with huge thick pins for high power ones. Next. Okay, so I'll start out with this was like a workhorse, high-speed fed op amp. This is actually was released at first before 1980. This is back in the 70s. You can see there's a lot of things this has that you still see in op amp schematics, and people propose a new op amp, discrete op amp design to play with. It's got a FET input, 5912s with a FET of choice, cascoded with another pair of FETs. This part, 1.7 gigahertz gain bandwidth and 1200 volts per microsecond slew rate and 100 milliamps out. This was a real power. I mean, you could take this and drive a headphone with it easily. Interesting thing though, it used output inclusive compensation. A negative thing is these typically had lots of headroom needed. Okay, and that's a big thing now. I mean, a lot of people complain about the op amps now and things, but a lot of the real applications now want rail-to-rail operation, extremely low power, the inputs to go to the rails, and all those things are really not possible with these discrete designs. But that's the real demand for the IC op amps now. So this is old school stuff. This had a quiescent power of 1 watt. That's why it was in a big T03 package. The only one difference here, and an interesting thing, is this uses a kind of unusual FET follower takeoff to drive the output stage. That's something you don't always see. Next. Okay, Teledyne Philbrick version, much more conventional Darlington second stage, You still have output inclusive compensation, but you don't have the FETs in this one at all. And here, and all the other things are fairly similar. This included a feed-forward compensation, so the compensation of this was a little more complicated than the one before. And they all had an option for external compensation to the output with pin 3 in this case. But this one had some internal feed-forward stuff going on. And so it was probably a little bit tweaky. Maybe this was designed by Bob Pease, I don't know. He was known for, sort of what I call Gothic designs. Lots of extra parts, lots of compensation components going here and there. Next one. Okay, yeah, this is the analog devices version of that. Interesting, went back to the FET buffered, a simpler FET buffer, but it's still a FET buffered output stage. A little question here, did anyone see how the short circuit current works? With just those diodes. Okay, so when you source or sink a lot of current, when you have a diode drop across the 9 ohms, you steal all the current. Okay, I said that because the next one does something differently. Any other points here? This circuit also introduced a bipolar cascode and not a FET cascode. Probably was cheaper. They all used the 5912, and they all had basically the same performance, but the circuits are, different. This is a sort of a slightly stripped down, a little cleaner one. Next. Okay, this is a lower output, lower power amplifier, very stripped down. This only uses 12 transistors. This is a very good candidate, even though this is, 30, 35 years old. The performance of this is pretty nice. I mean, this would make a pretty nice op amp even today. They got rid of active devices and used little tricks. Like R5 is like a little beta compensator, and R6 sort of gets, you don't have a cascode, so it gets the drain voltage exactly equal nominally. So the little tricks applied to get rid of active, transistors and things and make this cheaper. And the short circuit current is different because with a transistor Darlington, it gives you all the current. You can't just steal the current away because it gives you more and more and more. So you have to reach back and turn the bias off. And this also has drift and offset trim. One point about FETs is at 2 degrees of freedom, BP and IDSS. And then in any of these circuits, you can always trim the drift and the offset to 0, but there's no way to find that point automatically. It's an iterative thing. You have to measure the drift, compute the 2 trims that will give you 0 offset and 0 drift. That was done not with pots. That was done actually with people picking resistors and sticking them in one at a time. So these things that were expensive. Next. Okay, this is a slightly different take on that version. Here they don't have little resistor tricks to get rid of that. It was a nice, completely balanced current mirror. This is another very simple, straightforward circuit. I don't know why they use the gate to source junction of a FET for the short circuit sensor. That seems weird, and I speculate that those 1N4117s are very tiny FETs. They probably have a very high forward voltage. So it might have been that the short circuit current limit was asymmetrical, and if they got another couple hundred millivolts VBE, that it became symmetrical or something. But that's one of those tricks that, who knows why. Okay, next. All right, this is, I don't know where this dates from. It's pretty early. It's around 1970. This is a very early classic composite amp. I mean, you see these all the time. It's a cascoded JFET. This case uses a 301 with the pole 0 across the inputs. The classic way of making a composite amplifier. You could take a 5534, do the same thing. Any one of a number of things, and get pretty good performance. And in the instrumentation, and again, there's the resistors you select: TRW, 2, 3, 7, and 8. Those are places on the board where someone would sit there and plug them in. When actually, I think those are pins for a test fixture. You put it into a test fixture, do the offset and drift, and then you would pick them out of a bin and stick them in there. Okay, next. Okay, this is a very interesting composite amp. It uses an LM108, which is pretty slow op amp, very high DC gain at the input, but it has feed passed, And that 4416, the Q12, is really only a resistor that, it's connected as a resistor. It's as a resistor, but when you try to put too much current through it, it limits as you get on the saturation curve. So it's a current limiting resistor. But the main amplifier path is a FET follower driving a bunch of conventional gain stages and output states. This is kind of a way to make a composite amp that's quite a bit different. I suspect that the step settling of this amplifier is unusual because the LM108 is very slow and the other path is very fast. And so you tend to get pole zero steps when you're trying to use it looking at the settling time rather than just the dynamic performance. It's worth saying a lot of these circuits were designed for data acquisition. A to Ds were incredibly expensive. So what you do is you take a fast op amps and you multiplex lots of inputs on them. So the op amps are much cheaper than the A to Ds. So they wanted very fast settling op amps. We'll get to the HOS 50 soon. That one set the standard for a long time. It was 200 nanosecond settling to 12 bits. It was designed a long time ago. And people like Analogic who built medical instruments would tend to use one A to D and lots of amplifiers. There's another subtle reason for using only one A to D, and that when you're doing a CAT scan image, if A to D had different gains and things, the images had artifacts. So if you use one A to D, you get rid of the regular artifacts in the images because you have a different gain pass for different pixels. And so if you're one A to D, every pixel goes through the same chain. Okay, next. Okay, HOS 50 was really a popular product, did very well. At this point, I should have said this in the beginning. Walt Jung's history of op amps and the description of these circuits is available for free download from Analog. He goes much further back in history. I didn't, there's too much to cover. The pre-war effort and the wartime effort, pointing guns and all that. People were talking about operational amplifiers in the late 30s and early 40s and stuff. And a lot of that stuff was done with tubes. A lot of it was secret. Not all of it is available to show everybody. And in fact, a lot of these things, a lot of these discrete designs came after you called on customers who were doing secret work and stuff, and you saw what they were doing, basically, and you went back and said, okay, this is how they're solving their problem. Let's do it for them. Next one. Okay. TO8 hybrid HOS 50. This is the classic FET input high performance op amp. One thing it adds here is a cascoded. The second stage is a cascode, which helps the performance, and it has some feed forward. There's 100 puff feed forward around the Darlington, which helps with the speed. But with these component values, this hybrid would get, as I said, 200 nanosecond settling in 12 bits, which is really, really fast. It took a long time before we had ICs that did that. Next. Okay, here's one slightly different. That cascode is drawn funny, but it's the same thing. But you can see there's a pole zero step in series emitter of that cascode. I mean, all these things are tricks some designer decided would improve things. It's a lot of work to analyze, all of it. This one has clamping across the inputs. But in general, it was the same basic circuit and the same performance. Again, drift and offset trim with parts dropped in. Next one. And I apologize, this one's a little bit hard to, there might be a better one of these in Walt's, of this one in Walt's presentation. This is the actual original schematic. I have to thank a friend of mine, Adri Kallisfart. He used to work for Analog. Those careful reverse engineerings of Teledyne Filbert parts and that are all things he did. And it's all, these parts are all obsolete now. There's nothing, there's no point anymore in hiding the schematics. There's nothing real here commercial anymore. Okay, next. Okay, I threw in some what I call Gothic circuits here. The next one. Okay, now we start seeing somebody. I'm not sure what this adds to the party. There's little 1 and 10 puff capacitors everywhere, 4 puff capacitors. There's a FET feed forward, there's a FET source follower feeding something into the output directly off the input. And this, again, being from Teledyne Filbert, I think this is after Bob Pease left, but Bob did sometimes do things like this. He get them complicated and confuse everybody. Next one. Okay, Class A DMOS output. You never would have thought somebody was doing that back in the 70s. Interesting folded cascode driving it. That was one of their standard products. You'll also notice lots of these devices use nothing but 3904s, 3906s, 2907s. Just absolutely the most commodity devices you could get, all bought in chip form. Next. Here is an interesting amplifier. It has two inputs. It has a fast DMOS input, which is obviously going to have very horrible. Those are just DMOS FETs. They're probably horrible offset. They're not even matched pairs. They're just individual offset and drift. But there's a nice bipolar input stage driven by a 5912 dual source follower that provides a good DC good path, but slower. And those things are combined in the integrator into the second stage to make a actually fairly complicated composite amplifier. Now it's got some DMOS FETs thrown into. So I mean, this thing is an interesting study in just how complicated some of these things got that long ago. Again, it's got that the basic performance they're looking for is this 2 gigahertz gain bandwidth product and 1200 volts per microsecond. I don't know where that came from. That just happened to be like almost all of these have the same numbers, no matter what the design. I mean, so we got a nice part with 15 transistors does that. Why do you need this? I don't know. Next. Okay, here's quasi-complementary VFET output. Another thing, they were putting this in. This looks like an audio, some kind of somebody's idea for an audio op amp. But people were doing this stuff back around 1970. The VMOS FETs were available from Fairchild, and they had very high transconductance and no gate current, no base current. So people tried using them. And so they made modular products with them. Next. Okay, this is the most complicated circuit. I have no idea why all that stuff is in there. You can see it's got a very complicated quasi-complementary VMOS output. It's got a whole little amplifier thing off the output to drive the Q14, the pull-down VMOS, to give you the quasi-complementary behavior. And the top obviously is much more simple. The short circuit current, they actually have a thing where you can actually, pin 9 comes out and you can change the short circuit current value, but only, in both directions. Actually, they have a thing set on both directions. You can adjust the short circuit current so you could live dangerously and not have it if you wanted, I guess. Well, actually, there is a limit. You can't get rid of the resistor. It's internal, but you're probably intended to add more resistance. But this is a pretty interesting design for that time period. I mean, there aren't that many ICs that are that complicated in terms of op amps. Next. Okay, this is a change. This is part 3 of the talk. This is one thing I presented in that long thread about discrete audio op amp design. And this is my idea for a very simple signal path, one gain stage, same thing, one folded cascode gain stage, and just how good you can do 10 ppm kind of distortions on line amps with. This is op amp style with lots of feedback, right? But still, you can do a lot with some pretty simple circuits. So this is one flavor of the input. LSK389, the diff pair, and a cascode. J310 is a commodity FET still available, very high VP, so you can do the direct cascode connection. You don't need another supply. That matching current source thing on the bottom is for 2 reasons. One, the little 2-diode feedback thing to the emitter, like on U2 and U1, actually recaptures the base current of the cascode, so that the dynamic current is nonlinear. The CJC current is nonlinear in a cascode, and that's a very, very easy way to recapture it. I mean, there's a thing, the Huxford cascode, which has Zehners and some other devices and everything, but this does the same thing with almost nothing added to the circuit. So this is just simply, and those things on top have no, the current mirrors on top have they're gain of 1. They're really just folded cascode. Literally on one side, it's folded, and the other side drives with just a gain of 1. So you're not doing the normal like Hafler input where you're taking gain there, voltage gain there. This doesn't have any voltage gain there. So truly, the differential current from the input pair goes into the output node. Next. Okay, here's another one, fully complementary JFET one. Here, the J1 and J2 would be an N-channel diff pair. J3 and J4 would be the P-channel diff pair. And you can pick the resistors in between to give exactly the same GM. You can just drop this into the same circuit and get exactly the same behavior. A simple GM into a high gain node, which you put your comp cap there, or you could give yourself, next slide. There's the next one after this. Let's talk more about the whole circuit. This is no, this is right here. This is fine. This is just a simple output stage, not the world's most optimum thing. I said, we steal the bias from the front end. I'll show that in the next slide. I have some suggested part numbers. Those are surface mount transistor arrays. I actually built this with these values and verify that everything works and all. I get performance I expected, pretty close. Unfortunately, I wasn't able to get a clean new breadboard and actually take some nice measurements. I'll probably throw that in when I put this online. But it's a bootstrap Darlington output. It's biased up hot. We're into it. Even in a 600 ohm load, it's very soft compressive down in the air. There's no crossover at all. Just a very weak S-shaped curve, even at 600 ohm drive. If you want to drive 100 ohms, you have to maybe beef it up somehow. But the value's there. The whole entire op amp draws 25 milliamps. Yeah, next slide. Here's a suggested the whole thing put together. So now there you can see how the voltage from Q2 and Q9 there and their emitters is sort of borrowed to make a bias for the output. This whole circuit runs at 25 milliamps. It's designed to run at 15 volts. There are different ways of connecting the transistors on the FETs to get a different, standing current GM ratio. The compensation here suggested is 100 puffs on the to ground on the high gain node. Now, as Bob published, this circuit would work just like his. If you want to put a resistor to ground, use this thing open loop. It would work fine. I've done it. You just you set your gain by the GMR. You just set up a comp cap to the resistor to ground, and you can get a fairly decent open loop amplifier. Or you can do a combination of the two. And I've played around with that, right? There is some benefit in some cases of like getting a combination of open and closed loop behavior. Those components in red are optional. The cascodes are optional. You don't have to have them. They do help a little. The optional compensation components are you want to get really clean response unity gain. Actually, truly gain of 1 as a follower. It's a little. You can't just use the simple 1 capacitive compensation. For gain of 5 or gain of 10, it's fine. You just put a comp cap in there. You tune the comp cap to get your response. I'll have some slides of performance in there. And again, I built this on a couple little boards and it worked fine. Next. Okay, some people always want to know what's inside those magic Toshiba FETs. This is a real authentic Toshiba 2SK170, and it has lots of channels in parallel. It's brute force. That's how they get the low noise. It's big. Those are 100 micron bond pads. So you can tell how big that die is. I used to have a picture of this with one of our op amps sitting in the middle of it. And this is much bigger than the whole op amp. Next. Here's a little blow up of that picture to show those little square cells. Each one of those little walls is a channel. Okay, and then the drain and sources are interdigitated on the diagonal. So all those channels appear in parallel when you wire the whole thing up. And yes, it is gold. They are made with gold metallization. And I suspect the 74s are the same thing. The only differences are the fact that the P versus N, there's different capacitance issues and transconductance issues. It's actually probably physically impossible to make a perfect N and P complement. Exactly, that everything is complementary, like the capacitance and the transconductance versus current and all that. But I don't think that that's that important. Some people think it's more important than other people, but I think you can design around those things. Next. Okay, I got some performance slides. Go. All right, 100 puff comp cap, 600 ohm load. You could probably get it unity gain stable, maybe a little bit of tweaking, but you can see 10 ppm, plus or minus a little performance. Next. These are pretty boring, almost all the same thing. With a 25 comp cap and a gain of 20 dB, get a little bit of distortion performance. I apologize for it being I have a way with my spice to make the noise floor be 300 dB. So this is the second and thirds. Yeah, I believe those, and that's what it shows up when I actually measure the circuit. All those components down there, you can't see them, or I don't believe the simulation to that level. Next. Okay, that was the fully complementary circuit. This is the performance with the first circuit. That's the quasi-complementary input, and you can see it really doesn't change much. It's still doing better than 10 ppm, and so going fully complementary isn't buying it except for and the all N channel one can all be built with just stuff you can buy for cheap if you really don't have the money, can't afford it. I like to see everyone being able to participate. I don't like things where people have to go and buy $20 less components just to make something. Okay, next. Okay, take the load off. You don't get much more improvement. You do get better. Now the distortion's a little bit less, but you don't get a huge improvement just taking the load off. So the 600, so the output stage is really not contributing to distortion. Next. Okay, now I did something interesting. Okay, this is why I showed the noise. For some reason, I grabbed it, showed the sync. That's the numerical noise floor with the precision. So that's why it looks like that. The FETs, and I put 100 millivolts BP offset, and then trimmed it out back to 0. Distortion, nothing. The seconds don't go crazy. There's nothing. The distortion is almost identical within a dB. I made it in simulation, but I suspect reality is not going to vary dramatically. So, obsessive matching is not necessary. If you want to go back a couple slides to this big schematic. Okay. R4 and R1 and R5 and R55 on the bottom there could both have pots to the supply. And you have two independent trims, and you have a bunch of choices in this circuit. You can trim the offset and drift, both be 0. It is an iterative trim. I mean, you have to figure out how to measure the offset and drift. The offset's easy, the drift is not. But another thing you can do is I posted a picture a long time ago, so I'll go look it up again. I couldn't find it this last night. I posted it a couple of years ago on some thread. You can do the gain and the offset identically to 0 and infinite, respectively. So you can take this apart, and the gain will be absolutely 130 dB, and the offset will be 0, with two independent trims and with FETs randomly picked out of a bin. That's the important thing. So there's no, you can pick crazy different ones from 5 grades apart. But if you have a batch of C grade parts, you take any two of them out of a tube, and you could trim up the same result. So I mean, matching and not having trims is one way to do it, but the trim pots are awfully cheap. And if you buy 100 FETs to get 8 pairs, that's expensive. Okay, now go back all the way back. All the way back to those performance plans. Okay, there's one with, yeah, okay, up one. Up one more. No pedal, okay, that one was last. Okay, I quickly, last night in my room, I did a fancy of this part, because I realized I didn't have one. It's pretty clean. It's not super perfect. Coming down is that's from. I don't think, I mean, this is 150 volts per microsecond. I don't think it's in a real circuit, but you can see it's pretty fast and clean. Next. Oop, up, back up. It must have gone too far again. There. Here's the frequency response, a 20 dB amplifier. You can see it's pretty flat out to 3 megahertz. 3 megahertz or so, probably more than you'd want. You probably want to limit your bandwidth of the input somehow. But that's the bandwidth of the part. The open loop gain, this is without trimming the gain, trimming just the offset. The open loop gain is about 85 dB. But I said you can get this curve here just keep going down on that slope. I'm not a great supporter of like killing the open, simply killing the open loop gain is some kind of great benefit. Keeping your open loop gain thing pole beyond 20 kilohertz, because you can just take the trim pots and just move it anywhere you want. And I don't think that will make an audible difference, but that's my opinion, of course. Okay, next. Okay, here's something I threw in just a minute ago for the guys at Linear Systems. I had built one of these, an all-FET one of these, and when I was leaving to come out here, I was drilling a hole for the battery like this, and it seized. And the microphone went across the room and into pieces. And so I said, so I couldn't bring it. I was going to bring this as a demo. I have one of these built, interestingly, not with just all FETs, but with my optical bias strip, which you could use. Oh, she could use. This is a classic phase splitter for what's called a shelf microphone circuit. You put the capsule on there. It's got a bias voltage on it. I don't show that here. You trim the bias current. The trim is usually done to trim the second harmonic to 0. And if you look in the transductor in these books here, you'll find the article. The trim of the second harmonic is dramatic. It takes all the power supply noise out too, which I didn't realize at the time. So if you've got the second harmonic and all that intermodulation of the noise with the input disappears with you. I have pictures. It's dramatic. And here, if you want to use a classic bipolar PNP output, you have to use a fairly big coupling cap. Those are expensive. They're big. And if you want to make like something you want to sell to the audiophile audio engineers, you're going to have to do a half a microfarad special film capacitor. But I built mine because I use JFETs in the output stage. I was able to use 1,000 puff Teflon capacitors, which nobody could complain about. Okay. You roll that down. You grab, I don't know what happened there. You grab the picture and just pull it out. I don't know what happened.
Okay, no, didn't work. Sorry about that.
Okay. All right. Well, I don't know. Okay, just bring it back. We'll have to work. Okay. This is the. I must have done this. I must have screwed up. I just did it a minute ago. Oh, that one worked in the bottom. I screwed up the bottom one.
Back up and see if I can go forward. I can't.
Okay, never mind. Okay, well, the bottom is not much to show. So you sort of caught most of it. These microphones need a phantom power, typically 48 volts. They need a high voltage on the capsule. The capsule is not electric. It has to be externally polarized. What I use is what's called MOSFET. MOSFET drivers. They use a little tiny solar cell and a LED. They generate about 6 or 7 volts. And I took 6 of those, and the way I have it connected, the battery actually appears with it. So I have an optically generated 60-volt bias for the capsule. And by using JFETs in the output, I can use extremely large resistors, R7 and 8 for the gate bias, and so I can use a puff cap and still get way down the low frequencies. I have built it. It sounds really good. Still have 60-volt bias. I haven't published it, but you can do the patterns, capsules with patterns. But you can generate 2 of these 60-volt things, turn them off and on. So you can do pattern capsules. In fact, you can do a switch with a complete variable pattern capsule, all optically, no oscillators or charge pumps in there or anything. All the other techniques for generating the bias voltage have some RF on. You look at the chamber in there with an RF circuit, pumping up the voltage and everything. So that's a really neat circuit, and I put SJ74, the LSJ74s work just fine there. And the part I use is the AEB1121. It's not super cheap. It's not that expensive. So it's going to be a little bit more than a Colpitts oscillator with 1 transistor and a coil, but still, I think for the performance I'll fix the picture for you.
The obvious question, and I know you answered it in the article, but maybe not everybody has read it. 50 mega resistors, that's awful for noise.
There's no DC current. Yeah, and it also is rolled off at 1,000 puffs. Oh, I mentioned the article. Yes, the resistors are 1,000 puffs not for the AC coupling, low frequency. They're coupling way below that. They're there to roll off the noise of R7. Oh, the regular Johnson noise. They have no excess noise because there's no DC current. But yes, the Johnson noise is rolled off by the coupler cap. Right, and that was when you were on the phone. Those optical things would generate your voltages, your bed gains, if they only draw micro. Those things supply 25 amps. And there's ways of making them variable. Completely floating optically isolated variables. I've done all kinds of things. We've made an RF MEMS switch for cell phones that uses the optical. They have a charge pump in the cell phone. It's very hard. Very hard to keep the interference out of the cell phone. But with this, with the MEMS switch, they can do it with an antenna switch. And a demo of that is dramatic. It's an absolutely powerless. It's no power supply circuit that's running the switch. Use room light. I have one way to use room light. Yeah, use room light to turn the MEMS switch off and on. Oh yeah, these little PV arrays, you can buy them without the LED and by themselves, and even room light will light them up enough to turn the MEMS, because it identically draws no current. These things, APV, you looked at the web, it's a regular Mauser DG card, regular stock, it's Panasonic. I listed a whole bunch of them in my article, a whole bunch of sources. There's some that are hard to get that go up to 20 volts, but there's a whole family of ones that are 7 volts, which that's what the standard MOSFET switch needs an absolute minimum of 5 volts, so they have these 7 volt things. And actually, they make the solid state relays with them. They're made to make solid state relays, and sometimes, the only recently I've seen them like as a separate, they used to make them just for the solid state relay companies, like CT Claire. You put the giant triad in there, and you use this thing to turn it off and on. But they've started selling these, and they're a really neat thing, because you're just completely floating. It's not a lot of current, you don't want to draw more than a few microamps out of it. But for a fixed amount of optical power, if you vary the load, it directly varies the voltage. So if you put a load on it, by varying the current in the LED, you get a variable optically isolated supply. Okay, that's all I got.